So today we have our first seminar. We have an exciting lineup, and Tony Linero is gonna kick off our seminars. Tony is an associate professor in the Department of Statistics and Data Science at the University of Texas at Austin. His work focuses on the intersection of Bayesian and parametrics, machine learning, causal inference, and missing data. He received his PhD in statistics from the University of Florida, and he has been awarded many grants and other prizes. So we're glad to have you here. And he's going to talk about Bayesian machine learning for causal inference. So without further ado, the floor is yours. Just some ground rules. So we have until 4:30. Do you prefer questions during or questions at the end?
I'm happy, however, like whatever the cultural norms is. I'm happy to be interrupted, yelled at, sort of whatever.
All right, so let's take questions during, and then when it's 5 minutes before 4:30, I'm gonna let you know.
Okay.
All right.
All right.
Okay, thank you.
All right, thanks, Carlos. Thanks for the invitation as well. Wait, I can admit people into the thing. Okay. Yeah, so I'm going to talk about some stuff in Bayesian machine learning for causal inference. So Carlos invited me to do this, and I said yes, and then I sort of realized I wasn't sure what a good talk would be, and mostly doing kind of 25-minute talks at conferences. So it was an opportunity to kind of like consolidate my thoughts on some things, and I'm hopeful that, if people have feedback or, disagreements or whatever, that would be very, very welcome. And kind of moving on, yeah, so this is joint work with a collaborator, former colleague, Chan Zhang at Florida State University, and a few students from UT Austin, Angela Ting, an Integer alum, and then a student from UC Davis, Prabita Kundu, and yeah, supported by by an NSF grant. And I'll just lead off with the main point, which is what I hope to kind of convince you by the end. And that's that if you do Bayesian machine learning methods, if you apply them correctly, that they can be useful for performing inference for estimating treatment effect heterogeneity. And I kind of have three illustrations of this. I'm starting with what I view as kind of like the least controversial. I think hopefully everyone will be on board with the first bullet point, which is that it generally, applying Bayesian machine learning often kind of forces you to use good practice when you're estimating nuisance functions as part of like a larger traditional frequentist approach to estimating heterogeneous treatment effects. Then we'll talk about sort of practical Bayesian methods. So like if you actually want to not just use these things to estimate nuisance functions, but you actually want to do a full proper Bayesian analysis, that I find Bayesian machine learning and Bayesian methods as a useful way to sort of reason a priori about how to get good estimates of heterogeneous treatment effects. It sort of forces you to think about things in a way that at least I have found useful in constructing things that are stable and seem to perform better than other things. And then lastly, I'm going to go with something that maybe I'll get pelted with tomatoes by the end of it, but something about policy estimation and the Bayesian, what Bayesian inference says about these kind of cross-fitting ideas and post-selection inference. So that's the plan. Why is it? Okay. So I'll introduce a little bit of background first, and this is mostly just in case. So we're talking about treatment effect heterogeneity. When I say treatment effect heterogeneity, I mean you have some treatment of interest, and you're interested in learning something about how the effect varies across some subpopulations. So you might imagine a population of like canonical example of this in the context of an RCT might be something like precision medicine, where I have a population of individuals, maybe they all respond differently to the treatment, and I would like to assign treatment to those whom it benefits the most. Or maybe I want to assign treatment to people for whom the treatment is not harmful. I want to optimize the treatment that I assign. I think that's not too difficult of motivation. And then in observational studies, there's a few reasons you might want to do something like this. One is kind of policy estimation, meaning like I want to I want to suggest some policy for some sort of intervention, and that it can sort of lead to better policies if you take into account that certain subgroups might respond differently. So maybe I have a pot of money. I want to give interventions to schools that I think will benefit the most from some particular type of treatment, and I need to make some decision about which schools I'm going to give my money to. That's one reason to kind of be interested in these things in observational studies. Another is that, and this, I guess maybe a little bit of thinking and could be pushed back on to some extent, is that larger causal effects. So you actually have some incentive to find large causal effects because it takes larger amounts of confounding to explain away those effects. So I might be able to do a sensitivity analysis and maintain evidence for the effect of a treatment if I'm looking at a subgroup for whom I think that the causal effect is larger. So that's just motivation. And some notation just in case we're not familiar with the usual causal inference. I'm going to be using the potential outcomes framework. So I have some thing that outcome I'm interested in. Yi of A is the outcome I would observe for individual I under a binary treatment that takes values either 0 for control and 1 for treated. And then I'm going to write the potential outcome as a prognostic effect of covariates. So this is untreated. What would my prediction be for the potential outcome? And then a treatment effect for those who are assigned treatment. Then a little bit of an error. And we're going to assume observing data. So bold Y for all of the Ys that I observe, bold X for all the X's I observe, bold A for the treatments that I actually observe. So A is a vector of treatment assignments. Those are the actual observed treatments, right? So there's always one potential outcome that I don't see, but I see Yi of A for the observed value of A. And the goal is to estimate some summaries of this treatment effect function. That's what I want. I want, if not tau x, some interpretable summary of tau x. And I'm going to adopt these assumptions. I'm calling them axioms because I'm not going to tolerate criticism of them for the purposes of this talk. We're just going to assume that this is true. And I mean, we're looking basically just at simulated data anyway, so I know that these are true. But I'm observing Yi of AI. So the outcome I observe is the potential outcome evaluated at the actual treatment. That's called consistency. I assume basically no unmeasured confounding, meaning that my treatment assignment is independent of the potential outcomes, conditional on my covariates. I assume that holds for all X. And then I assume an overlap condition, basically that I always have some chance of receiving treatment. So these are standard assumptions. Of course, you would be interested in general in doing sensitivity to violations of them, but we're just going to take them as given. So the first point that I want to make is that Bayesian machine learning methods generally produce pretty good estimators of nuisance parameters. So the usual thing that one does when one is going for estimating heterogeneous treatment effects, at least if you want to operate in the standard kind of doubly robust framework, generally the idea is you start with an estimator that's based on an oracle that knows these two particular functions. It knows the mean outcome under treatment and control and my covariates, and the propensity score, so the probability of receiving treatment. So step one is construct some oracle estimator, and you can, like, if you assume that these two things are known, you can usually do a pretty good job at estimating the treatment effect. The second thing that you do is that you approximate the oracle. So you have an oracle that has good properties. You approximate it usually by applying some type of cross-fitting. So I split the data in half. Let's say I use half the data to estimate the mean outcome. I use half the data as well, the same half of the data to estimate the propensity score. And then I use the other half basically with these things, mu hat A and E hat, playing the role of the known, they're known versions in constructing the oracle. And then typically what will happen if you do some analysis is that the estimation accuracy of your thing, the tau hat that you end up at the end, will be equal to the estimation accuracy of the oracle plus a remainder term that behaves as the product of the two estimation rates. And so the idea, what you typically will hear is if I estimate, let's say that I'm estimating a finite dimensional parameter, that if I estimate both of these things at a rate faster than n to the minus 1/4, this will typically be of size root n. And so I will get something asymptotically that behaves the same as if I had known what the oracle estimator was to begin with. So there's multiple instantiations of this idea. And, Kennedy at CMU has this DR learner as a particular example. And then the R learner of Nie and Wagner are basically, can be roughly speaking thought of from this perspective. Now, if I want to, so the main point now is, how do I choose these nuisance estimators? I need to estimate these two things. I'm going to split the data in half. I'm going to estimate them. But what do I go about doing? Because if I tell you how to estimate these, then you'll be able to run through the whole procedure. You'll be able to construct your theoretically good estimator of the treatment effect. And the BART model has been like pretty successful as a thing that people use to do this particular step. And I'm going to try to sell this as, well, try to kind of explain why this seems to be a good thing to do and present some evidence basically that if you need something to estimate nuisance parameters, you often won't do much better than a BART model. But what a BART model is I have some outcome I'm interested in, and I model it as a sum of regression trees. I call it, like, another way, if you're familiar with XGBoost or boosted decision trees, you can kind of think about it as the Bayesian version of those boosting algorithms. So I'll express Y as a sum of decision trees with some normal error. And basically what you do is you just put prior distributions on each of the shapes of the trees and the predictions that the trees produce. So I'll have a prior on this tree and its predictions, prior on this tree and its predictions, and the G's just returned for you, depending on what your covariates are, predictions from the leaves, according to whether the X's satisfy this rule. And then you just do Bayesian inference on it, right? I can actually think of these trees as parameters. You can place a prior on them, and you can just grind the MCMC. That's a whole topic on its own, but I'll just let you know that that's a doable thing. You can, it's not too difficult. I'm going to present some evidence that it's like a reasonable thing to do. This is a table from a paper that I wrote some years ago, kind of pulling a bunch of these basically UC Irvine data sets, covering a variety of different sample sizes and numbers of predictors, comparing BART as just an estimator of the prediction function, a modified version that I'll mention in a second that is slightly better, and then boosting, lasso, and random forest. And the thing that's cool about the results in this table that I found is I didn't have to tune. There are default priors that basically make it so that the BART and the S-BART work without me tuning. So like a common criticism of these kind of bake-offs is, well, maybe you spent a lot of time tuning the things that you're promoting and not a lot of time tuning the other things. I actually spent way more time trying to get reasonable answers from boosting and the lasso than I did from the BART methods, which just use default priors. The numbers in the table are cross-validated estimates of root mean prediction error relative to the method that I was proposing called soft BART. So anything bold basically means that you win. And of course, the thing that I suggested ended up performing pretty well. It didn't always win, but it did a pretty good job. And BART was a close second. I'll make a 2-second pitch because this method isn't like super popular. So I'll just make a pitch. There's a paper. What it does is it takes a BART and it just sort of smooths it a little bit so that you get better performance when things are, when the underlying truth is smooth, you get a little bit better performance. In causal inference contexts, again, like these things have been used. So this is from a paper by Vincent Dory and others, summarizing results from the Atlantic Causal Inference Competition. So ACIC, well, I think maybe they have a different name now, runs these competitions every year. And it's basically, they set up some simulation ground truth and just have people submit things, and you kind of see what does best for the purposes of estimating causal parameters. For this particular year, the main determinant of whether you got a good result or not, at least in terms of bias in RMSE, was basically just whether your estimator used BART in a halfway sensible fashion. It seemed to be more important than other kinds of things, like whether you were doing super learning or whether you were doing this or that. It seemed like that, at least for this, that it was about what, how you were estimating the nuisance functions. Similar story. So this is bias in RMSE. I don't know how easy this is to see, but most of the BARTs are sort of over here, and then the non-BARTs are kind of over here. But whatever, this is just one year of the competition. A similar story for coverage, although the coverage story is a little bit more nuanced in that TMLE was tending to do a little bit better in terms of coverage. But a TMLE with a BART, as opposed to a TMLE without a BART. There have been other competitions. This is one from a more recent year. You always kind of have to, I would advise treating these things a bit skeptically, because BART or these competitions, they're always run by someone. They get to pick the ground truth, and maybe they're biased in some way. This particular year, it was run by Mathematica. And I don't think Mathematica has a bias towards Bayesian methods. They might, but like they seem to be relatively like an impartial third party. This particular one was estimating subgroup causal effects. And again, the methods that did best were the ones that used BART. So this slide was stolen from a different presentation. I'll shout out Samir Deshpande at U Wisconsin for his flex BART. Okay, so that's the evidence I have that it does well at estimating. Nuisance functions, there's, I can call scoreboard and point to places where it actually just does well in the only kind of reasonable way to evaluate these things. But what I think you can kind of learn about it is trying to figure out why exactly it is that the BART methods end up doing pretty well. There's a few things that BART does automatically that other methods don't do automatically that I suspect contribute to some extent with why they end up performing well. So the average nonlinear estimators, you get posterior averaging. And we know from, Breiman's work on bagging in random forests that averaging nonlinear estimators, all other things being equal, is a good way to reduce bias, or not bias, reduce variance. So this isn't really a particular to BART. There's nothing that, but none of the other methods typically, if you're looking at machine learning methods, if you're doing things kind of lazily, no one's going to force you to average things together. Like if you do XGBoost, it's not going to force you to build an ensemble of XGBoosts and average them. Whereas BART kind of like, there's no way to use it that doesn't actually have you do that. The other thing is that unlike boosting in random forests, there's an averaging that kind of happens in two directions, or ensembling in two directions, because BART itself is based on an ensemble. Every single sample from the posterior you have is an ensemble. We know ensembling is good. And so every iteration, every single, sum of trees is probably pretty good. But you're also averaging against the posterior. So you're sort of adding in one direction and then averaging over the posterior. So it does a little bit more averaging than the other procedures. It also focuses on low order interactions. And when you think about, at least the types of problems that I deal with, or you go back to your linear modeling class, how do you think about adding interactions in a model? Well, usually you start with main effects. You can throw in the main effects. And then maybe you start thinking about second order interactions. I'll add product terms. Pretty rarely do you go for third order interactions. and then it sort of decays exponentially from there. There's no guarantee that the world will kind of look like that, but it's like the standard modeling practice. And BART kind of forces you, again, to do that because it grows shallow decision trees. It aggregates a bunch of low-order interactions. Whereas something like random forests, it does aggregate things, but it aggregates a bunch of deep, high-order interactions. Like a single deep decision tree is a very complicated estimator. It's a very high-order interaction. For reasons that I don't quite understand, it seems like Bayesian modeling seems to respect high noise settings better. I don't know. I can't really give you a great explanation for why, but like something seems to be going on that makes it behave in high noise settings better than things like XGBoost, which ostensibly should be quite similar. But like gradient boosting, neural nets, these are all things that are known to not be great in high noise settings. And again, what I care about typically is high noise settings. And then there's this idea that maybe it's the rates. So if you go back, what do you need for these things to work? You have two nuisance functions and you need to estimate them both, and you're going to get the product rate. So you want to estimate these things at as fast a rate as you possibly can. And maybe BART does a good job at, maybe it has this quote unquote good rates of convergence. So there is some evidence that this is true. So there's two results that I'll cite, one from myself and Yoon Yang at UIUC, where we proved that in a particular class of functions with a sparse or additive sparse structure. So this is basically the setting of summing together a bunch of low order interactions, that if your ground truth looks like summing together low order interactions, we're able to get a fast rate of convergence. BART is adaptive to finding low order interactions. If you have high order interactions, that's like a very difficult estimation problem. If you have first order or no order interactions, you're basically dealing with a GAM, which is like you can get reasonable rates there. But BART is adaptive to the degree of interaction that's actually present in the data. This is a result for the soft BART model that I showed you a little bit of. And then this is also from Rakova and van der Pas, basically at the same time proved it for the original BART. I also conjecture, there's this highly adaptive lasso thing that gets claimed as, well, guaranteeing that these things all have n to the minus 1/4 rates or faster. If one puts a lot of stock in that, I believe that it's probably provable by someone who is better than me at approximation theory that BART would satisfy a similar condition. BART has been proven adaptive for a lot of function spaces, not this one in particular, but a lot of them. And based on the structure of like what's going on with this highly adaptive lasso, I don't see any major obstruction to being able to establish this. Although I don't have a great sense of how interesting people think that this type of result would be. It does sort of require that you buy into that it's the rates to find it interesting. All right, so that's my evidence that it's good for estimating nuisance functions. Some theory, some results from competitions, and has a good reputation for estimating nuisance functions. Now I'll talk about actually trying to leverage the Bayesian paradigm to try to improve the modeling for heterogeneous treatment effects. I have a case study here. Really, the only purpose of this case study is to generate some data-anchored simulations. So I'm not actually going to analyze any real data in this talk because I want to avoid having conversations about whether my thing is ignorable or not. So I know in my simulation studies everything is ignorable. But it's based on this data set called a large ongoing survey called the Medical Expenditure Panel Survey. And the proxy question we're going to look at is we're going to have a binary feature, whether someone smokes or not, and look at that as a cause of an individual's health status. So health status will be In the original study, it was ordinal, but I'm simulating it so that it's continuous. And that's caused by smoking, binary treatment. So a little bit more on where these data generating processes are coming from. One of them will come from a BART, basically one of the models that I'll talk about a little bit later, called the Bayesian causal forest. It sort of conforms to estimating a prognostic effect and then a treatment effect. Basically the same thing with a ridge regression instead. So I can replace a BART with a ridge regression. And then this other thing called an R learner with a lasso used to estimate tau. The details on this don't matter so much for the purpose of this talk. It's just another thing. So this is what happened, and it's like kind of surprising how hard, at least to me, it is to actually get good estimates of heterogeneous treatment effects. So I simulated some data. It happened to be simulated under the ridge, so a ridge regression model for the treatment effect. And I used what I think are 4 perfectly reasonable things to do. There's a Bayesian causal forest I'll talk about in a little bit. That's the BART version of doing things, fully Bayesian BART version. There's the causal forests, or causal random forests, which is like developed by Susan Athey and Stefan Vogger, pretty popular in the econometrics literature. There's the ridge, which is the truth. Well, this isn't the truth. Like, I did fit a ridge, but the ground truth was also a ridge. And then the R learner with the lasso. And they all, even though they're all kind of sane, they all say very different things about both the degree of heterogeneity and, you know, the, well, yeah, mainly the heterogeneity. So these are on the x-axis histograms of the heterogeneous treatment effects for the different models. You can see the causal forest, it's like way spread out. The R learner somehow just completely malfunctioned and nulled everything. BCF is slightly more concentrated than a causal forest, and then the ridge, which is fit to the truth, like this is a correctly specified model, is even more homogeneous. And you can see it's really tough. This is scatter plot of the truth against the estimate. And like, I mean, the estimates are basically they're almost uncorrelated with the actual outcome. You can see like the causal forest is basically uncorrelated. So you have the estimate on the x-axis, the truth on the y-axis, and it's like, it's not really doing much. Bayesian causal forest and ridge are at least pointing in the same, like if you squint, you can kind of see that they're positively correlated. But it's only like correlation of 0.2. So this is kind of a statement, I think, about what you should expect in practice. It's one thing to design simulation experiments where you jack up the noise level and then, you know, your machine learning method looks like it's recovering everything very well. But when you anchor it to data, you're often looking at things that look like this. So what do you end up kind of like taking away from this? There's not a lot of agreement on the degree of heterogeneity. And, you know, so where do you kind of go from here? What I would suggest is that you think very carefully, since the data doesn't seem to be particularly informative about the degree of heterogeneity, that you need to bring in subject matter considerations. You need to kind of think, you know, okay, can I at least ballpark how big the heterogeneity it is, and so I can bake it into something like a prior distribution and use it to maybe do a little bit better. Incidentally, I mean, this is only one data set. It happens to be the case that the Bayesian causal forest had the best performance, even better than ridge. It's only one simulation, but like it is at the minimum competitive. And then causal forest was, right, no, the one that nulled everything, the R learner was the worst, but the causal forest was like a distant third. Okay. So what should if you kind of think about things substantively, and again, there's no reason, like not all ground truths look like this, but the ground truths that I care about tend to look like this. Generally, you expect small treatment effects. Like I don't expect that, well, this isn't again, it's not universally true, but most things, if you look at the causal effect, you will find that the effect of those things is small relative to baseline confounders and controls that you would throw in. They also tend to be relatively homogeneous. So like in order of what I might expect something that looks like the ridge the most and the causal forest the least, where, I mean, if you kind of inspect this, you end up seeing that actually the causal random forest is so heterogeneous, it's predicting for some individuals a health benefit of smoking, which seems unlikely. So relatively homogeneous, likely to be associated with the treatment choice, which is going to motivate inclusion of propensity scores, which we'll do in a moment. And so a parameterization that makes sense in this context is that you want to decompose the treatment effect as an overall main effect plus a relatively weak interaction structure. So treatment effect heterogeneity, which is captured by this term tau tilde, should be quite small. How small? Well, you have a parameter basically to play with that you can turn up or down to control the degree of heterogeneity that you expect. But then to complete the prior, you can just set a normal distribution for tau naught after scaling the data, and then a BART prior for tau tilde with a small sigma tau. And if you reverse engineer what the Bayesian causal force does, it's basically exactly this. So this was the motivation for a lot of the choices that were made by the people who proposed it. And I guess unsurprisingly, in realistic settings, Bayesian causal forests tend to do very well. Just in general, I think it's important. I mean, this intuition carries forward to evaluating the various other frequentist approaches to estimating these things. So one thing that you might do that is not a good idea, as I'll explain in a moment, is estimate your causal effect by stratifying on the treatment. And if you do that, it turns out that you get this super wiggly line for an estimate of the heterogeneous treatment effect. But yeah, generally what you want is to shrink towards small effects and shrink towards homogeneous effects. And yeah, this was taken from the DR Learner paper of Kennedy. Okay, so I said Bayesian causal forest for a bit, and I'll just give my take on like what exactly it is I'm talking about. It's this BART model where I model the potential outcome as a prognostic effect, a treatment effect. For reasons, it turns out to be a good idea to not regress on the treatment itself, but its residual. So you fit a separate model for predicting the treatment assignment. And instead of regressing on the treatment assignment, you use the residual instead. And a treatment effect, and then you just throw BART priors at all of these things. And then you turn the crank and you see what you get out of it. If you look at this, so this method was introduced by Han Murray and Carvalho, I think 2020 in Bayesian analysis, something like that. And they actually also will drop the propensity score into the prognostic functions for reasons that they explain, but I won't get into. And like thinking Bayesian also kind of tells you what not to do. So I told you that what you shouldn't do is stratify. So don't fit separate models to treatment and control. If you did do that, this is what the method would look like. You would get tau x, you would define the treatment effect to be mu for treated minus mu for control. That would be the effect that you would get. If you just imagine that the mu for the control had a normal distribution with some variance A, and the treatment had normal with mean 0 and variance B, and because you stratified it, and these are taken to be independent, what you'll find is that the induced prior on the treatment effect is normal with variance A plus B. What this says is my prior thinks that the treatment effect, which is an interaction, right, with the covariates, is of larger magnitude than the main effects of those covariates itself. You probably don't believe that, and so you probably should not do this. So yeah, generally what you find is that if you use this model, you will find that the variability of the treatment effect scales with the complexity of the prognostic effect. And often you want to think of prognostic effects as being large and treatment effects as being small, so you don't actually want to do that. Another thing that you can kind of pick out, I mean, now this, I think for anyone who, does a lot of causal inference, you know that you need to control for propensity scores if you want to get methods that have good properties. But why should you do that from a Bayesian perspective? So I added the propensity score here, and I can just kind of show you what happens if you don't. So you can define a parameter that quantifies the amount of selection bias. And what will turn out to happen is that if you have even a moderately dimensional problem and you don't control for the propensity score, your prior will tend to concentrate on models that believe there is no selection bias. So this would also happen if you use this t-learner stratifying on the covariates, provided that you don't control for a propensity score. And yeah, so this is kind of pernicious in the sense that imagine I'm throwing in a lot of predictors. It's because I think there's confounding, right? If I didn't think there was confounding, well, it might just be because I want to use those as effect modifiers, but like usually or often what you're doing is trying to control for confounding. And what this prior would say is the more confounders you have, the less you believe that selection bias was a thing that you should have believed in the first place. Why would you be controlling for all of these confounders if you didn't believe that there was, non-negligible selection bias? And so for that reason, you want to control for propensity scores. And the way that you control for it often comes out in the wash at the end, but definitely should be doing that. Now here's a surprising result. This is from a slightly different simulation setting, and it's in this paper from 2023. And the main takeaway here is that often when you're trying to estimate these HTEs, it can matter more that you get the shrinkage right, that you regularize things correctly, than getting the model right. So let me explain what's in this table. This is it's like a more complicated simulation, it's in the context of mediation. But there is a BART model that we proposed, and you could either have you could fit a BART or you can fit a linear structural equation model. That's like a linear model. So those are the two things that we're comparing. And then we also use those models to give you ground truths. So unsurprisingly, if the ground truth is a BART, you're going to do better than the linear model. That's not surprising. What was surprising to us was that when the ground truth was a linear structural equation model, fit to the data without any kind of penalization, we were still doing better. And my immediate reaction to this was, this is impossible. We fit, this is the truth. How can you fit this model? And the wrong model is doing better in terms of RMSE. But what the explanation is that, again, this is a data anchored simulation. We generated a ground truth by fitting things to data. And the fit to the data was such that actually you would rather get the model wrong and shrink correctly than get the model right and apply it without shrinkage. Another thing that's kind of surprising about this setting is that this was not a small data set. I mean, it's 15,000, which, I mean, okay, it's not massive, but it's not negligible. And there were only like 10 covariates. So you'd be thinking like, okay, I'm fitting a linear model. I have, with the interaction terms, I have like 20 parameters. I have 15,000 observations. I shouldn't have to apply penalization to estimate this thing stably. But it turns out that you do. And then to kind of confirm this, we reran it with another linear ground truth that was estimated not without penalization on the linear model, but with penalization using an R learner. And we found the effect was even more magnified. So this kind of convinced me that it really was the shrinkage that was doing it, and that you would rather shrink correctly than get the model right. Okay, so I have some beliefs, and these might be wrong, but I believe them. I strongly suspect that if you were really, really good at theory and you designed a BCF correctly, it would have doubly robust properties. There's probably something that someone in the future, maybe AI, can figure out how to solve this. I don't know. But that's a belief. There's no obvious reason to me that it shouldn't. We're doing something sensible with the propensity score. So like we should be able to do this. And I don't know how to prove it. And it seems hard, right? I think Ad van der Vaart made like partial progress on not even this, but average causal effects, and didn't get all the way there. So if he can't do it, I probably can't do it either. As I understand, you give your first year students the van der Vaart. That's a tough book. So I feel for you. Yes.
So in this literature, when they proposed adjusting for the residual propensity score, the motivation was not directly doubly robustness property, it was just empirical observation.
Okay. So I have a confession, which is that I added this term. They didn't have it. That was why I did it. But no, this is kind of make it sort of yeah, they just dump it in here. They don't have this term. They just dump it in here. So but yeah, the debiasing term, I'm like, oh, okay, yeah. I get the point that now the motivation for not necessarily doing the residual, but wanting to regress on the propensity score in particular, you can justify that as saying, right, if I erased that propensity score, I'm going to end up in this setting, and I want to avoid that. The most natural way to incorporate the propensity score will be something like a linear adjustment in here with the propensity score. So like, if I was going to do it without doing a residual, I would do something like A plus alpha plus beta E hat X instead. But yeah, you caught me. I was trying to be sneaky. Or I didn't, the real explanation is that I took this slide from somewhere else and I didn't feel like changing it. Okay. So now I guess I don't have a ton of time. I'll talk about policy estimation a little bit. And this is where we're gonna kind of go off the rails a little bit, or maybe, I don't know. You all seem pretty low key, so maybe you'll just accept it. But yeah, I'll motivate, because I think another takeaway from this picture is like, gosh, estimating HTEs is really hard. Maybe I should set the bar a little bit lower. I think I can do average causal effects reasonably well. Maybe what I should do is subgroup effects. Like kind of, maybe I want to estimate a causal effect in like a relatively coarse set of subgroups. So that's kind of linked to this policy estimation thing. I might want to get a coarse policy for assigning treatments to individuals, and stole this from Athi and Vogger. They have a paper on doubly robust policy estimation. And yeah, the basic idea is that you look at covariates and you use it to assign treatment. There are a bunch of reasons you might want to do this. One is like if people are in the field implementing treatments, like if doctors need to assign treatments, then it makes sense that they should, that having a decision tree that's nice and interpretable would be good for them. Could also be budgetary reasons. There's also equity reasons, like you might not want a highly detailed or non-transparent machine learning algorithm that tells you how to assign treatments, but you might want, again, just kind of something more interpretable. So the formal framework for this is that you have some policy assignment function, rho. It's going to take your covariates. It's going to decide whether you're going to be treated or control. And we're going to assume that what I want is a policy that looks like a shallow decision tree, say depth 2 or 3. So that's what I want. I'm going to assume basically that what I want is to maximize the outcome. I want to find the treatment that makes the outcome as big as possible. That would make sense if you were like doing dollars, like if Y was a dollar amount. And then I'm going to assume that there's some cost of the treatment. So like it's not free to assign treatment, so I'll assume that there's some dollar cost that will that I'll have to account for in assigning the treatment. So what I'll do is I'll define the utility of the policy as basically the expected value of the thing that I get. So I get, if I'm treated, I get Y1 minus eta to control for how much it costs. If I'm control, I just get Y0. and then rho x is just the picking out which policy. Up to a constant that's going to be equal to the expectation of rho x times tau x minus eta. And then the goal is just going to be to argmax the policy over the class of decision trees. There's this, for the sake of time, I won't go into detail on this, but there's a doubly robust procedure that Athey and Wagner proposed for doing this, basically based on this idea of kind of using pseudo outcomes. And then computing a decision tree is actually hard if you're trying to maximize things exactly. And so it turns out that this is doable in basically polynomial time with respect to the depth. Now, ostensibly, this has better properties than doing a naive plugin estimate, which basically, I have this thing, I'll just replace tau x with the estimate, like some non-parametric estimate of tau x. Now, what would a Bayesian do in this context? What a Bayesian would do is write a utility function. So we have this utility function here, and I would maximize its expectation conditioned on the data. So I do maximum expected utility. It's called a Bayes estimator, is an estimator where basically I define a utility function and I just take the expected utility and I maximize. For this particular thing, it turns out that the optimal thing to do is to use what I call the plugin estimator. So just optimize this expression, which is the plugin. So just get your Bayes estimators, throw them into the utility, and then do the optimization. And I think if you're competent, it should work basically just as well. Let's skip over this. It turns out I did a little experiment with causal random forest to kind of try to make this point. The doubly robust, this is a misspecified model. The doubly robust method and the plugin method are basically doing the same. You do somewhat better with the plugin, but it's kind of like a little bit more spread out. So now the kind of interesting part, which is usually you don't want to just do, usually you don't just want to get a policy. What you would like to do is estimate the treatment effect within the different leaf nodes. So I want to know what the causal effect is in this group, in this group, in this group, in this group. Now, how should I take into account the selection mechanism? So we estimated this decision tree using data. And if you look at this thing from the traditional frequentist standpoint, this you immediately identify as a post-selection inference problem. So what the frequentist line would be is this is a post-selection problem. If you want to do inference in the leaf nodes, you probably need to collect another data set, or before constructing the policy, cut the data in half and do something like that. Estimate the policy on half, estimate the treatment effects on the other half. The Bayesian standpoint is basically the posterior is the posterior, and we're going to completely ignore all of the post-selection inference stuff. So what should I do? The frequentist line is you can't ignore the selection. That's wrong. Your coverage will be wrong, right? There's no reason the Bayesian method should cover, right? We know they're not doing the same thing. Why should they cover? Do the responsible thing and split your data and do that. The Bayesian says, well, you trust your prior, right? And actually, this is kind of a counterintuitive point, but I think it actually says something. Even though I'm data dredging, even though I'm using the data twice, for Bayesian calculus to work, there have to be ground truths where I can completely ignore selection, and it will be accurate or conservative. There are ground truths where things will be accurate or conservative, because when I average my 95% over the prior, I have to get 95% back. So just choose your prior so that the actual ground truth is one of the good ones. Think hard about your prior, write it down, make the ground truth one of the good ones, and then the upshot, you don't have to throw away half your data. Just get to use all of it. So people do this, which is surprising, meaning my friends do this, like Carlos and Jared, and they do this in like Nature papers. It's crazy. Like I find it interesting. What they say is they use the data once. They got the prior, they use the data to get the posterior, and then they're done. So they use the data once to get the posterior. Everything else is from that. I don't completely believe it, but well, you can try it. And actually, for the data that I simulated, it actually works. So ground truth was a linear model. I fit a Bayesian linear model. I data dredged. So like the reason that this should not have good coverage is basically the treatment effects in the treatment groups should be optimistic. Like part of the reason I found these subgroups is probably because I got lucky in that the observations were like a little bit more larger than they should have been in the treatment group. But I picked the prior carefully, and I got actually higher coverage, lower interval length, and then all of the other methods data split. And so they actually are guaranteed to have nominal coverage. So all of the other ones get exactly 95% coverage in the big, like because of the way the data was generated. And there's no guarantee for the Bayes method, but we ended up doing it. Now, the thing that's interesting is that it depends critically that you did something sensible with the prior. So what I did in this case is I modeled the treatment effect as linear. Beta will have a normal prior with some scale parameter, and the scale parameter has an exponential 1 prior. That was how I kind of generated this. And it completely breaks down if you use flat priors. Not completely, but you get like 80% coverage, which is like back in the world of that's not working, right? And you can get exact 95% coverage by data splitting. Coverage goes off a cliff if you use flat priors. The role of the shrinkage parameter is basically you increase it. Generally, the coverage decreases as you increase it. But the cool thing is we could actually figure out from data what to do. We used a prior on it, so we were able to infer from data the appropriate amount of shrinkage and then got good coverage. So the story is like kind of shrinkage from the prior stops the subgroups that you estimate from being overly optimistic. And I have simulations for this, but I don't have the figure. Like okay, I'll take that. I lost it. Okay, so that's all I really wanted to say. So good nuisance functions, I think that should be like, okay, I hope you believe me about that. I hope you got at least some intuition on why you might want to have good like why Bayes might tell you something about what a good HTE looks like. And then I gave you an interesting take on post-selection inference. And I want to be clear, I'm not saying do this. Like, I'm not saying be this guy, but I'm saying like sometimes it works and it's weird. It'd be great if you could be this guy, and maybe if you're crunched like tight on data or something, you can afford to be this guy from time to time. All right, that's all.
Thank you. That was right on time, so we have time for questions.
Yeah.
I have one. Sorry, I have one that's a little bit in the weeds, but if I remember correctly, that method that has Richard, Carlos, and etc. in it, there is kind of this discussion about whether you should feedback cut or estimate jointly.
Yeah.
My vague recollection is that this is feedback cut.
Yes.
And so, I mean, I don't know how much the audience actually knows the difference between the feedback cut
Yeah.
And the joint estimation. But I was wondering if you could speak a little bit to that, because, for example, that's one of the reasons why the theory here is going to be particularly hard, I think. But well, I don't know. So do you have any thoughts about
yeah. I actually think that
why it's important and how
so the feedback cut is, so the reason, right, I think if you like ask them, they would tell you, I doubt they're that worried about getting bias from feedback. I think it's pragmatic for the most part. Now, there are these like kind of weird situations in causal inference where it's actually better in certain situations to use an estimate of the propensity score. Like frequentist, it's better to use estimates than use the actual propensity score. So there's some frequentist argument for maybe what you should do is use you should estimate it first and then plug it in. But that's a frequentist motivation. They have this point that what they're really doing, we had talked about G priors before, like when we met one-on-one. And what they're doing is not that different from using a G prior, because the prior for a coefficient under the G prior that depends on the design, and no one really has problems with G priors. They're using the design as well because this isn't fit on Y. So like they don't risk cheating or anything by looking at by estimating a propensity score, right? They're not using Y to do that. So there is a way to write down the prior in such a way, like as a G prior, and be kind of fully Bayesian kosher. The prior is arguably not that natural. I'll grant that. And I also think that in high dimensions, it probably reverts back the other way to you'd rather, if you knew the propensity score, I think you'd rather use that. But I think it's mainly just practical. Yeah. Don't want a nice modular inference. Yeah.
Any other questions in the room? So we have a question online. I'm going to read it for you. So I guess this is related to your last example. So the frequentist approaches is a 50-50 split. And we average frequentist results by averaging over many splits. Can we split up converters by using each split twice? Can we have a very be 300 split?
Yeah, so I was trying to think if there's a way to do this. I mean, like so I mean, the issue with using like a cross-fitting type thing is that if I split the data in half and I get a policy, then I actually have two policies, right? I use half the data. The estimate changes across the two. So I split the data in half, I use half to construct the policy, I use half to estimate, and I'd like to flip the roles back, which is what they do, right, in all the R learner stuff, right, or all the double machine learning. It's not immediately obvious how to do that because you'll get different policies if you do that. That doesn't mean there's not a creative way to accomplish a similar goal. It might be possible to split the data in half, use half the data in one way, use half the other half in like a symmetric way, combine those to get one policy and somehow keep the inference all kosher across the whole thing. I couldn't think of a way to do it, but it's plausible to me that that's a doable thing.
Any other questions? Right. So no questions, we are exactly on time. So let's thank the speaker.